MF is given by E reduction minus E oxidation. This is Shiny Creates Online School. Today I take you through ACK Diocese Mumias Chemistry Paper 2. Work with me as I take you through from the first question to the last question in details. Welcome. Question number 1. The following table gives the standard electrode potentials for a number of AV reactions. We have AV reaction for zinc. Its electrode potential is negative 0.76. AV cell for iron 2. Its electrode potential is negative 0.44. Then we have silver AV cell. Its standard electrode potential is positive 0.80. Then copper positive 0.34. The question says draw an electrochemical cell for the reaction that would give the least EMF. So when you're given this kind of a question, we just take the difference between the standard electrode potentials for these different cells based on how closeness they are. And in my case, I'll arrange them based on how they are supposed to be, or electrode potentials are supposed to be in the number line. Like in my case here, I have the most negative being zinc, negative 0.76. Then I have iron 2, negative 0.44. Then I have copper with positive 0.34. And lastly, I have silver with positive 0.80. So when I try to look at this question, I notice that zinc is close to iron 2, iron 2 is close to copper, and copper is close to silver. And now I take the differences. When I take the difference between zinc and iron, I obtain positive 0.32. When I take the difference between iron 2 and copper, I obtain positive 0.78. And when I take the difference between silver and copper, I obtain positive 0.46. Students, you know how I'm obtaining these differences. We know EMF of a cell is given by E reduction minus E oxidation. E reduction means the cell that undergoes reduction. E oxidation means the cell that undergoes oxidation. So in the first case, I'll take negative 0.44 minus negative 0.76, and when that is when I will obtain positive 0.32. And the rest, I still apply the same concept. And then, because our question says that we draw an electrochemical set for the reaction that gives the least EMF. Now we have the cell that gives the least EMF is a combination of zinc and iron cell, iron 2. So in this case, I'll just choose it, and I'll first write the cell notation of the two cells, and I will place the one that is undergoing oxidation on the left hand side and the one that is undergoing reduction on the right hand side. So I will begin with zinc solid undergoing oxidation to form zinc 2 ions, aqueous. And then we have a salt bridge to give us, we have iron 2 undergoing reduction to obtain iron metal. So with this particular cell notation, I can comfortably draw an electrochemical cell just by copying what I have on the cell notation. So zinc half cell on the left hand side. So I'm going to have zinc half cell on the left hand side. Allow me to have it a bit on a lower level. And the one for iron, I place it on the right hand side. And then I can begin by placing the electrodes, placing the electrodes. Then after placing the electrodes, I can introduce the solutions. So this is iron solid, and this is iron 2 solution, aqueous. And most of the times we are not limited to just say it is 1 molar concentration because they are standard solutions. Then this is zinc solid, and this is its solution, zinc 2 ions aqueous. Again, not limited to say 1 molar concentration for this solution. Then after that, I'll connect my 2 half cells with a wire connected with a voltmeter like this. Then I introduce a salt bridge that connects the 2 solutions to bring about the balancing of ions. This one I label it salt bridge. Salt bridge. Then this one is connecting wire. Is connecting wire. And you can still show the flow of electrons, but that's not very necessary in this question. So having this kind of a diagram, you earn a total of 3 marks. You earn a total of 3 marks. So you need to understand that the one that is more positive is the one that is placed on the right hand side, and the one that has the most negative electrode potential is placed on the left hand side. And this is because if I was to work out the EMF, the difference, I realize that the electrons flows from the one that is losing electrons. So the direction of the flow of electrons is from the one that is losing electrons, and as a result we place it on the left hand side, the one that undergoes oxidation. Now we move to the next question. Determine the EMF of the cell in Roman 1 above. Learners, we have 2 options here to work out this question. The simplest is the one that we take the formula EMF is given by E reduction minus E oxidation. What does this mean? I've said that E reduction means the cell that is undergoing a reduction. And the cell that is undergoing reduction between zinc and iron, automatically it is iron 2. Iron 2, when you look at it, it is more positive as compared to zinc. Therefore, it is the one that is going to undergo reduction. So in this case, I'm going to have negative 0.44 minus 0.76. And when I work this out, I obtain positive 0.32 volts. That is method 1 that we can use to work out the EMF. We also have an alternative method, learners. The alternative method is whereby we try to rewrite these particular equations. I'm writing the one on zinc and iron. When you look at zinc and iron, you realize that all the equation has been written in a reduction form or in reduced form. But when you begin, you realize that the one that is undergoing oxidation should not be written in this form. So how I do, I interchange that reaction, I reverse the reaction, so that zinc undergoes oxidation because the one that is supposed to undergo oxidation. So what am I supposed to do? I begin with zinc, solid, undergoes oxidation to obtain zinc ions and lose 2 electrons. And because its site was negative, it also changes to a positive. Therefore, I'm going to have positive 0.76 volts. And then the one that undergoes a reduction should remain the way it is written because it's written in a reduced form. So we have iron 2 ions plus 2 electrons. I obtain iron 2 solid. And the EMF remains negative 0.44, negative 0.44. And then I add everything in this particular equation, and I obtain the electrons cancels out, and I'm going to have zinc solid plus iron 2 ions aqueous. I obtain zinc 2 ions aqueous plus iron solid, and then when I add the 2 positive 0.76 plus negative 0.44, I still obtain positive 0.32 volts. So this is another method that you can use to obtain this answer. So we have 2 alternative methods, and the first one is the simplest. Learners, you can choose the best for you. So this is the longest method, and it's used especially when you are taught to write the overall equation when the 2 cells are combined. It is the method that you usually use to work out that kind of a question. Moving to the next question, select the strongest oxidizing agent and you give a result. On the beginning, or when we are beginning this question, we talked about the cell that is most positive is always referred to as the strongest oxidizing agent. And therefore, the one that is most oxidizing agent, as you can see in this list, it is silver with positive 0.80. So we select it and just say silver. You can still use the formula because they have used it. That is 1 mark. And the reason that we give it is because it has the most E0 value as the most E0 value of positive 0.80. So this gives you 1 mark and the explanation gives you 1 mark. On the other hand, the most or the strongest reducing agent could be zinc because it has the most In this case, it is the most positive. The most positive has the most positive E naught value of positive 0.8. On the case of zinc, it is the strongest reducing because it has the most negative E naught value of negative 0.76. Moving to the next question. In the production of aluminium from aluminium oxide, 100 amperes was passed for 6 hours and 40 minutes. Determine the mass of aluminium obtained. So this is electrolysis of aluminium oxide, and we know at the cathode there is always deposition of the metal. So basically, the reaction that occurs at that particular cathode is aluminium ions gaining an electron to obtain, of course, 3 electrons because it's losing 3 to obtain aluminium solid. If that is the case, we need to know the amount of this aluminium that was deposited. This is the application of the law that leads to determination of the mass, relates the mass of a substance and then the electricity that is passed. So in this case, Faraday's talked about this amount of substance and the electricity passed, or the quantity of electricity, being directly proportional. And learners, we have the formula that we usually use to simplify this kind of an equation and work it out in a very short time. And the equation that we always use, we say mass is given by the Q, or quantity of electricity, multiplied by RFM, or relative formula mass of that substance. We divide by the charge of that metal multiplied by the Faraday, or the constant. With this formula, we can simply be in a position to determine anything that we do not have, be it the Q, be it the RFM, be it the C, or be it the F. What we are given here, we are told that we have 100 amperes was passed for 6 hours and 40 minutes. So we need to understand that first we need to work out the Q. And the Q is given by IT, where I is the current and the T is time in seconds. So I'm going to have current 100 multiplied by time, which is 6 hours. We have 6 hours times 60 to convert into minutes, and times 60 to convert into seconds. Then we have 40 minutes again plus 40 minutes to convert these 40 minutes again into seconds. Then later we multiply by the 100. So we have 100. We multiply by, when you take 60 times 60, 6 times 60 times 60, we shall obtain 21,600. Then plus 40 times 60, it is 2400. Then we first add the 2. Then we multiply by 100. So it is going to be 100 multiplied by, when you take 21,600 plus 2400, I obtain 24,000. 24,000. So I multiply by 24,000. And when I work this out, I obtain 2,400,000. 2,400,000. And this is C, or coulombs. So that is our C. That is our Q. Now with our Q, I can just go and substitute it directly. So I'm going to have now mass shall be given by 2,400,000 multiplied by the RFM of aluminium, which is 27. We divide by the C, or the charge of aluminium, which is 3. Aluminium has a charge of 3 positive, so it is 3. Multiply by the F, which is the Faraday's constant, which is 96,500. 96,500 coulombs. So when I work this out, learners, I shall obtain 223.83 grams. And that is the simplest way to work out this question. The simplest way to work out this question. It is the simplest because sometimes you may be given the mass, the Q, the RFM, and the F, and you don't know the C. So with this formula, you can even work out the C without even noticing the nature of the metal that was used. So it is the simplest method to work out this kind of question on the determination of the quantity of electricity produced and the relationship with the mass produced at the cathode. When we are given the substance being a gas, learners, we need to understand that if the substance is a gas, like in the case of the preferential discharge, whereby we discharge the hydroxide and we obtain water, oxygen, and some electrons, which are always 4. The formula is just replaced by volume, which replaces the mass, is given by, we have, instead of now writing, we have Q. Now instead of writing the RFM, we always write the molar gas volume. We divide by now the number of electrons, not charge now. The number of electrons, these electrons, 4 electrons, then we multiply by the Faraday, and still we shall be in a position to work out that particular question when the product is a gas. So this is one of the simplest ways to work out and determine the quantity of electricity and even the quantity of a substance that is produced either at the cathode or the anode. So learners, that was the correct answer. So this 1 mark, this 1 mark, and the answer 1 mark. Let's proceed to the next question. Define primary cell. What is a primary cell? We know we have those cells that once you use them, you cannot recharge them. And those are the cells that we refer to them as primary cells. For instance, we have the dry cells, the leaf clenched cell. So a primary cell is a cell that cannot easily be recharged after use. Is a cell that cannot easily be recharged after use. A good example is a dry cell. Then we have a fuel cell. A fuel cell, on the other hand, is not a primary cell. It can be recharged by adding more raw materials. So it's a cell that converts chemical energy of a fuel and oxidizing agent into electricity. Is a cell that converts chemical energy of a fuel and oxidizing agent into electricity and oxidizing agent into electricity. So in other words, we have conversion of a fuel which is in chemical form carrying chemical energy into electric energy. Like a good example is hydrogen oxygen fuel cell. Oxygen is the oxidizing agent and hydrogen is now the fuel. So hydrogen carrying the chemical energy is converted to electrical energy by being oxidized by oxygen. So in this case, that is what we call a fuel cell. Next question. Give one reason for electroplating. Electroplating is process of coating one metal with another by use of electricity. And why do we have to do coating? Most of the times we do coating for metals that do corrode too fast. And again, as a way of beautifying these particular products. So one of the reasons why we do electroplating is to improve the appearance of the material. So we do this to improve appearance. We also do this to prevent corrosion. So one is enough to prevent corrosion. For instance, if I coat iron with copper, I electroplate iron with copper, then I'm trying to prevent corrosion or rusting. So any 1 mark. Let's move to question number 2. What is fractional crystallization? If I have a mixture of two salts and I have to separate them, I will apply the knowledge of separating these salts and a method that we call fractional crystallization. But these two salts should have different solubilities in the solvent at a given temperature. So fractional crystallization is the process of separating two or more crystalline salts based on differences in their solubility in the same solvent at given temperatures. So we say is the process of separating two or more crystalline salts separating two or more crystalline salts based on their differences in solubilities in the same solvent at different temperatures or at given temperatures. That is what we call fractional crystallization. So you find a salt that is soluble at this temperature and the one that is not soluble. So with that difference in solubility, we can separate one of the salts. So let's move to part 2 of this question. The table below shows solubilities of salts A and B at various temperatures. We have solubilities at 50 degrees Celsius and solubility at 20 degrees Celsius. A at 50 degrees Celsius, 86 grams of it is already in the solution. At 20 degrees Celsius, that one of it is already in solution. B, at 50 degrees Celsius, 18 grams of it is already dissolved in the solution, so that's solubility. And B, solubility at 20, 8 grams of that particular salt B is already in solution. And then we are told that a mixture of the salts containing 29.5 grams of A, so I go to A and write it, 29.5 grams of A, 29.5 grams of A, and 16.25 grams of B. 16.25 grams of B. At 50 degrees Celsius. The mixture is cooled to 20 degrees Celsius. Determine the mass of the salt that crystallizes. So having written the masses of the mixture at the respective solubilities. So I want us to begin with A. A solubility is 86.86 grams and I'm only having 29.5. So 29.5 of this salt is the one that is the amount that I've been given. So, and the solubility is 86, meaning solubility 86 means it has that capacity of dissolving 86 grams of any salt, and I'm only given 29.5. So 29.5 are already in solution, so they are dissolved in the solution. Then solubility is that one, and I only have 29, so they are already in solution. So no crystals in this case. So A, we can conclude no crystals. Then I move to B. I'm given solubility is 18 grams, and I'm given 16.25. So these, all of them, they are already 18. So that means they already dissolved, and even the solution needs around 1 point something more still to dissolve, because I'm having 16.25 and it can accommodate 18 grams. So I need even 1 point something more still to be accommodated in the solution. Then I have 16.25 on the other hand, and the solubility is 8. Solubility, this solution can only accommodate 8 grams. So this means that if it can accommodate 8 grams, and I have 16.25, the rest zenye ziko juu, they will be in crystal form. They will not be having any room in that particular solution. So they will just form solid or crystallize, or there's going to be crystals in this case. So if now the question, determine the mass of salt that crystallizes. So we know B crystallizes, and we have seen at 20, we can see we have around 7 point something or 8 point something which have not been dissolved. So the salt that forms crystals is salt B. Salt B crystallizes. So to determine the mass, we are going to take the mass that you are given. We are given 16.25, and then the one that was supposed to dissolve was 8. So in this case, I'm supposed to get the crystals that were formed, or the salt that was left undissolved. So in this case, the answer becomes 8.25 grams. And that is the correct answer to this question. Moving to the next question. Explain how the use of ion exchange resin removes water hardness. We know ion exchange is one of the methods of removing water hardness, whereby we use a medium packed with sodium ions, and then we pass water that contains either magnesium ions or calcium ions. So we are going to explain this and say add water containing either magnesium ions or calcium ions is passed. So add water containing either magnesium ions or calcium ions is passed through a column containing sodium ions as a resin. So sodium ions here are acting as the resin that is going to remove or to exchange with the calcium or magnesium ions. Sodium ions exchange with calcium ions. Sodium ions exchange with calcium or magnesium ions, which are responsible for the hardness. Which are responsible for the hardness. The calcium ions and magnesium ions are retained by the resin. The calcium ions and magnesium ions are retained by the resin, while sodium ions are released into the water. While sodium ions are released into the water, making the water soft. Making the water soft. So that's how we use ion exchange to remove water hardness. This explanation gives you 2 marks. Part C of this question, name 2 disadvantages of hard water. Hard water has several disadvantages. It does not lather easily with soap and therefore it wastes soap. So you can say waste soap because hard water forms scum with soap. Waste soap because it forms scum with soap. You can also say it forms scale in pipes and boilers, reducing their efficiency. Forms scale in pipes, especially those pipes that transport hot water, and boilers, leading to their blockage. And in case of the boilers, it reduces their efficiency in the process that they are being used in, or the activity that they are being used in. So any two gives you 2 marks. Part D of this question: state and explain the observations made when aqueous ammonia is added dropwise until in excess to a solution of copper 2 nitrate. Learners, we need to understand this is qualitative analysis, again applied in paper 2. And we need to understand the formation of precipitates when we use aqueous ammonia. Aqueous ammonia, when it's used, it tries to test the presence of zinc ions and also the presence of copper 2 ions. When I add a few drops of ammonia solution and a white precipitate is seen, then I cannot make a conclusion because we have very many ions that form white precipitate with a few drops of ammonia solution. But when I add in excess and the white precipitate dissolves, then I can make a conclusion that it is zinc ions which are present, because it is only zinc ions which are white or forms white precipitate that dissolves to form a colorless solution. The rest, they form white precipitates, but their precipitates do not dissolve. For instance, we have magnesium, we have calcium, we have lead, barium, and the rest. They form white precipitates with a few drops of magnesium or ammonia solution, but when I add in excess, or when you add in excess, it do not dissolve. So the only one that dissolves in excess to form a colorless solution is zinc ions. In the case of copper, adding a few drops of ammonia, it forms a pale blue precipitate. Adding more or in excess, the blue precipitate dissolves to form a deep blue solution. So we are being taught to state and explain the observations made when aqueous ammonia is added dropwise until in excess to a solution of copper 2 nitrate. So we are going to find that addition of ammonia dropwise to copper 2 nitrate leads to formation of blue precipitate. Addition of ammonia solution dropwise to copper 2 nitrate leads to formation of a blue precipitate. Excess ammonia to the precipitate, to the blue precipitate, leads to formation of a deep blue solution. And then after stating this, we explain what has really happened. So the blue precipitate is due to formation of copper 2 hydroxide. The blue precipitate is due to formation of copper 2 hydroxide and the deep blue solution is due to the formation of tetraamine copper 2 ions. Tetraamine copper 2 ions. Tetraamine copper 2 ions, they are blue in color. The complex salt, so complex ions in solution, they are soluble. And that's what you are supposed to write, and this gives you a total of 3 marks. It's due to the formation of tetraamine copper 2 ions, which are deep blue in color. You can just say which are deep blue in color. The tetraamine copper 2 in the formula is Cu. Tetra means 4, so 4 molecules of ammonia, and then it's a complex salt with a 2 positive. So this is what we call tetraamine copper 2 ion. Moving to the next question. State Gay-Lussac's law of combining gas volumes. The Lussac's law, as applied in the mole concept, states that when gases react, they do so in volumes that bear a simple ratio to one another, and to that of the product if gaseous. So, for instance, if I have gas A plus gas B to obtain gas C, looking at if I add 20 of this gas, 30 of this gas, and 20 of this gas, looking at the mole ratios in terms of their volumes, I can have 2 volumes of this gas, 3 volumes of this gas, and 2 volumes of this gas based on what I've been given. So I can easily use this to balance the equation because these are 2 moles, 3 moles, 2 moles. So if the product is the gas again, I can just use their mole ratios using the volumes and determine or balance the equation that leads to the formation of the product. But now we are applying this question given different volumes. We are being told that 100 cubic centimeters of propane was ignited in 180 cubic centimeters of oxygen and the gaseous product allowed to cool. Determine the volume of the residue gas. So we begin here by writing the equation. Propane, it is C38, C3H8, it's a gas. I react it with oxygen, which is a gas, and I obtain carbon dioxide and water. These learners take note that the product was allowed to cool, so we expect this to be in form of water, in form of liquid. So the only gaseous product is carbon dioxide. So when I try to look at what we have been given, we are being told that 100 cubic centimeters of propane was reacted with 180 of oxygen. 180 of oxygen. And we are not being taught to determine or the amount of carbon dioxide that was produced. So looking at what we have, I can begin by first balancing the equation. According to what we have, we balance the equation carbon 3, carbon on the other side is 2, is 1, so I try to balance it. I put a 3 here, and then for hydrogen 8, hydrogen I make it 8, I put a 4, I balance the equation by putting a 4, and then for oxygen I have 6, 6 plus 4, 10, so it's supposed to be 10, so I put a 5 here. As per what we are given, we need 1 mole of ethane to react with 5 moles of oxygen. And because oxygen is 180, there is no way we can say now ethane should be 100, and then when you look at 5 times 400, it's supposed to be 500, so we cannot have oxygen being limited factor in this case. The only thing that should be limited is supposed to be, all of these particular substances should be enough for the reaction to proceed. We should not have any of these two limited. So in this case, I have 180 and 100. So in this case, I'll ask myself, if 5 moles for oxygen requires 180, what about 1 mole? 1 mole will require how much? So it's 1 times 180 divided by 5, and this gives me 36. So I only need 36 for 1 mole. So I need 36 cubic centimeters to react with 180. So oxygen here is now the limiting factor. It is 180, so no excess. So the one that was in excess is now ethane. So if 1 mole is 36, 5, 180, 3 moles will be 36 times 3, and that gives us 108. Because now you can see it is now 1 is to 5 is to 3. 108 cubic centimeters. And now, with this piece of information, we have a given amount of ethane or propane that has not reacted. So, to get the residue gas, the volume of residue gas, so to get the volume of residue gas, we shall take the excess of propane plus the product. So the excess of propane, so we take propane which was in excess. So we only use 36, so we were given 100 minus 36, and this one gives us an excess of around, we have 64. Then the residue gas, the volume of residue gas becomes now 64 plus the product of carbon dioxide, which is 108, and this gives us 64 plus 108 gives us 172 cubic centimeters. That is the correct answer to this question. Part B of this question, what is empirical formula? Empirical formula, students, is the simplest whole number ratio of atoms present in a compound. Is the simplest whole number ratio of atoms, or that shows the presence or the number of atoms present in a compound, of atoms present in a compound. For instance, if I have C6H12O6, this can be simplified further to obtain CH2O. So this is now what we call the empirical formula, the simplest whole number ratio of atoms present in a compound. Looking at Roman 2 of this question, vitamin C, which is ascorbic acid, contains 40.92% carbon, 4.58% hydrogen, and 54.50% of oxygen by mass. Determine its empirical formula. When you are given this question, of course, you need to arrange and have a table that leads to determination of the empirical formula. So we begin with elements. Elements that we begin with carbon, hydrogen, and oxygen. After the elements, we move to the percentage composition. Percentage composition gives us, for carbon, 40.92, for hydrogen, 4.58, for oxygen, 54.50. After the percentage composition, we move to their relative atomic masses. Relative atomic mass of carbon is 12, hydrogen is 1, oxygen is 16. After that, we move to the moles. How do we determine the moles? Moles is given by, we take the percentage composition, we divide by the relative atomic mass. So we take 40.92 divided by 12, 4.58 divided by 1, and 54.50 divided by 16. And then we determine the moles. The first, for carbon, it is 3.41. For carbon, it is 3.41. For hydrogen, it is 4.58. And for oxygen, it is 3.41. Then from there, we proceed to mole ratio. Mole ratio, we look at the moles that we have, then we divide each by the smallest. The smallest is 3.41. So this is 3.41 divided by 3.41. It is 4.58 divided by 3.41. And it is 3.41 divided by 3.41. The mole ratio here is 1 is to, when I divide 4.58, I get 1.34. 1.34, and then this is 1. So in this case, where we have 1.34, we always advise to multiply by 3 across. Whether it is 1.33 or 1.34, we are always supposed to multiply by 3 across. So when I multiply by 3 across, I'm going to have 3. When I multiply 1.34 by 3, I shall obtain 4. I shall obtain 4. It is 1.34. 1.34 multiplied by 3, I'll get 4.02. So this is basically 4. And then this is 3. So the empirical formula now becomes empirical formula is C3H4 and O3. So that is the answer to this question. Learners, we have several instances where we need to do multiplication. We do not get our own number. When you get 1.5, you multiply by 2 across. When you get 1.33 or 1.34, you multiply by 3. When you get 1.25, you multiply by 4. When you get 1.20, multiply by 5. When you get 1.67, multiply this again by 3. When you get 1.75, multiply by 4. When you get 1.1 or 1.9 or anything 0.1 or 1.9, round off. That's what you are supposed to do when you are working this kind of a question, and you find that one of the moles, they are not giving you a whole number. So when it is 1.5 multiplied by 2, when it is 1.25 multiplied by 4, when it is 2.5 or 3.5 multiplied by 2. So those are cases where you need to do the multiplication across the moles that you have obtained. Moving to the next question, Roman number 2. Given that the experimentally determined molecular mass of ascorbic acid is 176 atomic mass unit, determine its molecular formula. So the 176 atomic mass unit is similar to the molecular formula mass or relative molecular mass. So once you have already obtained your relative atomic mass, it is always very easy to obtain the molecular formula. Once you have the relative or empirical formula, it is easy to obtain the molecular formula. So we already have our empirical formula. Our empirical formula is given by C3H4O3. And when you have this, you put N to represent the number of times these atoms are in a molecule. And you equate with the atomic mass unit or relative molecular mass, which is 176, first to obtain the N. When you work it out, you need to know that we multiply by the relative atomic masses by these atoms, that the number of atoms that we are given. For carbon, we have 12 multiplied by 3. Hydrogen is 1 multiplied by 4. Oxygen is 16 multiplied by 3. When you do the summation, you shall obtain 88. So C3H4O3, we already have the N. We already have the N. We already have the total. We do not have the N. That is what we are looking for, 176. So this 88 into N is what is giving us 176. So our N is equivalent to 2. And therefore, with our empirical formula C3H4O3, we multiply by N, which is 2. So our molecular formula is C6H8O6. And that is our molecular formula. Molecular formula. Moving to part C of this question. A solution of calcium nitrate is made by dissolving 16.4 grams in 2 liters of solution. Calculate the concentration of nitrate ions in moles per liter. Given that the relative atomic masses of calcium is 40, nitrogen is 14, oxygen is 16. In this kind of a question, we need first to determine, because we are given the mass of calcium nitrate that was dissolved in 2 liters, we can determine the molarity of this given solution, that the mass was equivalent to 16.4. So we start by looking at the moles of calcium nitrate. Moles of calcium nitrate is given by taking the relative formula mass, the mass divided by the relative formula mass. So the relative formula mass, we shall determine it by taking calcium mass 40 plus nitrogen 14 times 2 plus oxygen 16 times 3 and then times 2. And this gives us a total of 164. That is the relative mass. So if this is the relative mass, we can obtain the moles of calcium nitrate in 2 liters that you are given. So moles is 16.4 divided by 164, and we obtain 0.1 moles. So this 0.1 moles were in 2 liters, so per 2 liter. So molarity of this solution, or per liter, it shall be, well, these were 2 liters, so per liter it shall be 0.1 divided by 2, and it shall be 0.05 moles. So now molarity is per liter. So if it is the case, now that you have the molarity of this solution, we can now determine the moles of nitrate ions, or the concentration of nitrate ions in moles per liter. So if I could write the ionic equation for this reaction, calcium nitrate which is aqueous, dissociates to give us calcium ions, aqueous, plus nitrate ions. You realize that we have 2 here, calcium ions, calcium 1, so I have to put a 2 here. So according to what I have, it's 1 mole is to 2 moles between calcium ions and nitrate ions. But the moles of these are the moles of the calcium nitrate. So to get the moles of nitrate ions, because they were 2, according to our equation, supposed to be moles of nitrate ions shall be the 0.05, which is per mole per liter, we multiply by 2 because it had 2 moles. So in this case, we shall obtain 0.1 moles per liter. So that was the concentration of nitrate ions, which can be also 0.1 molar. That was the concentration of nitrate ions. That was the concentration. Moving to the next question. Question number 4. Give the UPAC name of the following organic compounds. Give the UPAC name of the following organic compounds. Learners, when you're given this type of a question, you can have your own summary somewhere. Open the compound and try to see how the bonds are arranged in that compound. So like in my case, I can see I have carbon. This carbon is attached to 4 methyl groups. Carbon attached to 4 methyl groups. So with this kind of a formula, I can decide which one is the longest carbon chain. I can decide it is my longest carbon chain. I can decide it is my longest carbon chain. Or moving up to down, I can decide which one is my longest carbon chain. I can also decide. So with this, I can see that if I can decide that this direction gives me the longest carbon chain, then it gives me 1, 2, and 3 carbons. And at carbon number 2, we have 2 branches of methyl. So this means that this is 2 dimethyl propane. 2,2-dimethyl propane. So learners, I can confidently give the name 2,2-dimethyl propane. These learners take note that whenever you start with anything back here, this letter should be small letter. So it is 2,2, and the numbers are separated by a comma, and the number and the letters are separated with an hyphen, and this gives us 1 mark. Then we have the second one, carbon 3 methyls, then bromine. So I have carbon, methyl, maybe another methyl here, and then the bromine here, the bromide here at this point. So again, I decide this one is my longest carbon chain, and therefore methyl and bromide becomes my branches, and therefore when I'm naming it's 1, 2, 3. So it is a propane, that is the parent chain. It's a propane again, and just 2 branches, different branches. So in this case, I have bromo and methyl. B comes before M, so I'm going to have 2 bromo, 2 methyl propane, and again this gives you 1 mark. The next one is HCCH2CH3. Again, you try to open it. We have 4 carbons. So I have 1, 2, 3, 4. And then I try to arrange them the way they have been arranged. So this carbon will carry a nitrogen. The second last carbon will carry 2 hydrogens. The last carbon, 3 hydrogens. And that's all. But now I ask myself, a carbon atom should be stable by having a total of 4 bonds. So I ask myself, where am I supposed to place this? What am I supposed to do so that I balance these carbon bonds? So I notice that in between these 2 carbons, we only have a problem. We need to balance these carbons. If I put another bond here, it becomes 3. For the first carbon and the second carbon, if I add another bond, all the bonds become stable. All the carbons become stable. The carbon 1 and even the carbon 2 with 1, 2, 3, 4. So when you look at it, it is now the formula that you should be having. So if I should name it, then the longest carbon, the longest chain, the parent name is butane. But because it is having a triple bond, it becomes a butyl. And now considering the position of the double of the triple bond, it becomes but1I. So the name is but1I, considering the position of the triple bond on the first carbon atom. So it is but1I, and this gives you 1 mark. Part B of this question, describe how this formula that we have said is 2,2-dimethyl or 2-bromo-2-methyl propane is distinguished from the two, that is the but1I that we have. But1I that we have. We need to understand that the bromo that we have, it is an alkane. 2-bromo-2-methyl propane, it is an alkane. It is a compound of alkane. Alkanes are said to be saturated. Then this but1I, it is an alkyne and it is unsaturated. Unsaturated is because of the presence of the double or triple bond. Saturated, only a single bond between the carbon atoms. How can I distinguish between the two? We have several methods, and one of the best methods to use is the chemical test of these two substances. And the best chemical to use is an oxidizing agent that we call acidified potassium manganate 7. So if I use acidified potassium manganate 7, which is purple in color, for saturated compounds, it do not decolorize, but for the unsaturated, it decolorizes. Please learners take note that I cannot use acidified potassium dichromate 6 simply because this is commonly used to oxidize alkanes. But for the double bonds, it rarely changes. So in this case, I'll choose acidified potassium manganate 7 and add in each case, and then I take note of the color changes. If it is decolorized from purple color decolorizes, then that is an alkyne. If it does not, that is an alkane. So we are going to say add acidified potassium manganate 7 to both. Add acidified potassium manganate 7. Please learners write in full. Potassium manganate 7 to both. In 2-bromo-2-methyl propane, in 2-bromo-2-methyl propane, potassium manganate 7 remains purple color, purple color of potassium manganate 7 or acidified potassium manganate 7 remains. while in but 1I, while in but 1I, while in but 1I, potassium manganate 7 will colorize. While in while in but 1I, acidified potassium manganate 7 will decolorize. And this is one of the chemical tests that we do between saturated and unsaturated compounds. So stating this gives you 2 marks. Moving to the next question. Ethyne can be prepared by adding water to calcium carbide. That is how we prepare ethyne or alkyne. The first alkyne is ethyne, and we react we add water to calcium carbide. Write an equation for the reaction which occurs. So calcium carbide is written like this. It is always a solid. Then I add water, which is a liquid, and the reaction occurs and gives us ethyne, which is a gas at room temperature, and calcium hydroxide. Considering the issue of valences, put a 2 there, and this is aqueous. When you look at the equation, it's balanced. Calcium 1, carbon 2, carbon 2, hydrogen 2, hydrogen, we have hydrogen 2, we have hydrogen 2, hydrogen 2 here. So those are 4. Hydrogen in this case are 2. So I put a 2 here. Hydrogen 4, oxygen 2, oxygen 2. And the equation balances out. So this is the equation to be balanced, have the correct state symbols. So this gives you 1 mark. Roman 2, explain why ethyne may be collected over water. Ethyne is usually collected over warm water, and this because it is lightly soluble in water and it do not react with it. It is slightly, because it is lightly soluble in water and it do not react with water. It do not react with water. Again, 1 mark. Next question. Give 2 uses of ethyne. Give 2 uses of ethyne, which is the first alkyne. Ethyne is used in welding and cutting of metals. Ethyne, can say, used in welding and cutting of metals. It is when it is mixed with oxygen to form acetyl, the gas that leads to the burning, or the gas that leads to, that is used in welding, acetylene. This another use for ethyne. It is used as a raw material in making industrial chemicals. Used as a raw material in making industrial chemicals, And you can also say it is used in manufacture of plastics. Used in the manufacture of plastics. Also used in fruit ripening. In absence of ethyne or ethyl, it can still replace it and be used in fruit ripening. All these are uses of ethyne. Part D of this question. Draw the structure of all organic compounds with molecular formula C5H12. So when you're given this kind of a question, just begin by having the first compound with a straight chain. So the first one we have 1, 2, 3, 4, 5. Then we add the nitrogens. So we are being taught to draw, we are not taught to name, but this is supposed to be propane. That is the first one. The second one, we can have an isomer of the cell, whereby we can remove this carbon with the 3 hydrogens and bring it to carbon number 3, or to this carbon, we replace it with this hydrogen. So we are going to have 1, 2, 3, 4. So after cutting it, I bring it to this carbon, this point here, and form a methyl. At this point. Then I balance the hydrogens that were supposed to be there. So this is the first isomer of pentane. So this becomes 2-methyl butane. You can still have the branch being CH3. So it's not a must that you open the branch. It will still remain to be a structure. Then another one, the third one, we're going to have a straight chain of 3. 1, 2, 3. And then I bring one carbon here and another carbon here. It forms a cross. Then I have the hydrogens of the branches. So this becomes, then I have the hydrogens like this. And this one becomes 2,2-dimethyl propane. 2,2-dimethyl propane. You're not being to name like it, but we can still name for clarity. This is pentane, the first isomer. The second isomer is 2-methyl butane. The third isomer is 2,2-dimethyl propane. So this gives you 3 marks each, 1 mark in each case. Moving to the next question, question number 5. The diagram below shows part of the periodic table. The letters used do not represent the actual symbols of the elements. Study it and answer the questions that follow. This is a periodic table portraying the first 20 elements represented by letters. And as we can see, this forms group 1, this forms group 2. These are the transition elements. Then we have group 2, 3. Then we have group 4. Then we have group 5, group 6, group 7, and lastly group 8. Then we have period 1, period 2, period 3, period 4, and maybe period 5. Compare the first question. Compare the trade in atomic radius between element D and E. We have element E and E. Learners, you can begin by trying to place or position the elements based on the number of protons. It is 1 proton, 2 protons, 3 protons, 4 protons, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and then 20. We can still use the periods and the groups to identify the electron arrangement of each and every element that we have. So we compare the trade in atomic radius. D is position 15 in the periodic table. E is position 17. Looking at their respective arrangements, 285 and this is 287. We are trying to look at their radii, comparing the atomic radius, and because they're in the same period, these elements have different radius or radii. And we know as the number of protons increases, the nuclear charge also increases, and that increases the atomic radius. So the stronger the nuclear attraction, the smaller the atom, and the smaller the radius. So in this case, we shall say the atomic radius of E is smaller. Despite having more protons, its radius is smaller because of more protons and strong nuclear attraction, making the atom to be very small, because the outermost electrons are strongly attracted on the positive nucleus, making the atom to appear smaller. So we first give the statement to compare. So we say the atomic radius of E is smaller than that of D. The atomic radius of E is smaller than that of E. Please remember that of D. That of D. Please remember to use comparative term, smaller than that of D. Reason: E has more protons. E has more protons, and hence higher nuclear charge than D. And hence higher nuclear charge than D. Therefore, higher nuclear attraction. So if it has an higher nuclear charge, it has increased nuclear attraction. That makes the atom to be small. And that is enough to give you 2 marks. So just use the protons that leads to increased nuclear charge. And that brings the difference. So statement 1 mark and the explanation another 1 mark, and that gives you 2 marks. Roman 2 of this question. What name is given to the elements in the same group as element H? We have element H. We have 4 major families and we have groups in this particular periodic table. The first group is group 1, where we find a family that we call alkali metals or alkali metals. The second group comes from group 2, which we call alkaline earth metals. The other group comes from group number 7, which is halogens. And the last one comes from the 8th group, which is noble gases. So that is the last family that we have in the periodic table. But now we are told to name what name is given to the elements in the same group as H. H, group 1 members, they have a family that we call alkali metals. So this is alkali metals, not alkaline, alkali metals. For alkaline, it is group 2, alkaline earth metals. So alkali metals, 1 mark. Then we have Roman number 3. Write down the formula of the oxide of E. Oxide of E. Where is E? E is 287. Position number 70, 287. So E 287, meaning its valence is 1. And we are looking at the formula of its oxide. So the oxide of E, we do not use the valence 7. The most stable one is usually the one that uses the valence being 7. So we can write this formula in 2 ways. The first way, it is E oxide. E having 7 gives this 7, and this takes the 2. Sometimes if you know it is chlorine, you may find a student writing Cl2O7. And we have another way. We can still use valence 1, whereby E picks 1 and oxygen picks 1 and E picks 1, E picks 2 and oxygen picks 1. So it becomes, or you write it Cl2 oxygen. So all these are correct formulas for this particular element, the oxide of this element. And element F is found just above element D in the periodic table. Write down the electronic configuration of F. Where is D? You can see D. So F is number 7, and its electron arrangement, if it's 7, the electron arrangement of F is 2, 5. Is 2, 5. All is usually fluorine. Fluorine. Select the most reactive nonmetal. The most reactive nonmetal is one that is the smallest in group number 7. So the smallest is not labeled. It's supposed to be the one with 9 protons. But in our case, it is E, because it is the one which is in group 7. So E is the most reactive nonmetal. If another one was there, I said D is supposed to be nitrogen, number 7, yes. Then number 9 is supposed to be fluorine. If fluorine was there, then it could be the most reactive non-metal. But because we only now have chlorine, which is E, is the most reactive non-metal. Give two uses of G. G is position number 10. It's a noble gas. It's supposed to be, we have neon. We have neon. So the uses of G, some of the uses of G, which is a noble gas, used in advertising signs, used in advertising signs. You can also say it is used in TV tubes. You can also say it is used in lightning arresters. Used in lightning arresters. You can also say used in high voltage indicators. So any two are correct and they give you 2 marks. Question number 7. But before we move to question number 7, from this periodic table, you may be told to identify the element which is most electronegative. The most electronegative element is the one that has the highest ability to attract shared pair of electrons towards itself. And most of the times is the most reactive nonmetal. And the most electropositive is the one that has the tendency to lose electrons. And most of the time, it is the most reactive metal. So if I was to choose the one which is most electropositive, I could pick it here, and the most electronegative, I could pick it at group number 7 at the top. Moving to the next question. A sample of chloride of C was dissolved in distilled water. Both red and blue litmus papers were dipped into the solution. State and explain the observation made. The chloride of C. C is position number 13. C is aluminium. So aluminium chloride, when it's dissolved in water, both the red and litmus papers and dipped into this solution, what are we expected to see? Aluminium chloride in water. Aluminium dissolves in water to produce an acidic solution. So we say the blue litmus changed to red and red litmus remained red. So blue litmus paper changed to red and red litmus paper remained red. And while aluminium chloride dissolves in water to form aluminium ions, which hydrolyze with water or react with water, which hydrolyze with water to produce hydrogen ions. To produce hydrogen ions. The presence of hydrogen ions then makes the solution acidic. The presence of hydrogen ions makes the solution acidic. So you need to understand that aluminium chloride, after it hydrolyzes in water to form aluminium ions, it is these aluminium ions now which pulls or makes water to break down into hydrogen ions and oxygen oxygen or oxide ions. In this case, the oxide ions are pulled by hydrogen, and aluminium ions pulls the oxide ions, and hydrogen ions are left in the solution, making the solution to be acidic. So this explanation gives you 2 marks. Part B of question number 4. The table below gives information on 4 elements by letters E, F, G, and H. Study it. Answer the questions that follow. The letters do not represent the actual symbols of the elements. Looking at the elements that we have, E has an electron configuration of 282, and this is magnesium in the periodic table. We need to have the real name for this particular element. Its atomic radius is 0.136. Its ionic radius is 0.065. So you realize that the ionic radius is smaller than its atomic radius. F is 287. 287 in the periodic table is chlorine with atomic radius of 0.099 and ionic radius of 0.181, and this is larger. The ionic radius is larger than its atomic radius. Then we have G, which is 2881, atomic radius 0.203, ionic radius being 0.133, and this ionic radius is smaller than the atomic radius. Then H2 2 is to 8 is to 8 is to 2, which is having atomic radius of 0.174 and ionic radius of 0.099, which is again smaller. The ionic radius is smaller than its atomic radius. For G, it is potassium, and for H is calcium. And you can notice that we have 3 metals and 1 nonmetal. F is a nonmetal. E, G, and H is there are metals. So looking at the questions that we have, the ionic radius of H is smaller than its atomic radius. Explain. So why does metals have smaller atomic radius, a smaller ionic radius than their atomic radius? So what happens? Metals ionize by losing electrons. And when they lose electrons, there is an increased nuclear attraction because of increased nuclear charge. And when the charge increases, the remaining electrons are strongly pulled to the central positive nucleus, and that makes the ion to be larger, to be smaller than the atom, or the atomic radius to be larger than the ionic radius. So we say H ionizes by losing 2 electrons. H ionizes by losing 2 electrons, and this results into to increased nuclear charge for the ion, and hence increased nuclear attraction to the remaining electrons. This makes the ion or the ionic radius to be smaller than the atomic radius. This makes the ionic radius to appear smaller than the atomic radius. This statement gives you 2 marks. Please, learners, note that this is the only explanation that we use when relating atomic and ionic radius for metals. So if I was to explain the same for G and even for E, I could still use the same explanation. When an atom loses electrons or it ionizes, it leads to increased nuclear charge, or the ions experiences increased nuclear charge, and that increase in nuclear charge makes the nucleus to be more positive, and the remaining electrons are then highly attracted to the central positive nucleus, and that leads to the ion appearing or experiencing stronger nuclear attraction, and it appears smaller than the original atom. And that is the reason as to why atomic radius of metals is always larger than its ionic radius. Moving to the next question, write the equation for the reaction between E and chlorine. E in our case is 2H2, and I said is magnesium. So I'm going to write E, which is a solid. I should know that elements that have less than 4 electrons in the outermost energy levels, they are metals. So it's a solid plus chlorine. When writing chlorine, I should also know that it is a diatomic element, and it is a gas at room temperature, and it gives me E chloride. Learners, I say that when you're writing the formula, first write the way the electrons or the elements are. So I write E and Cl. After writing E and Cl, because that is supposed to be the product, I look at the valence of E. The valence of E is 2, because it loses 2, and the valence of chlorine is 1, because it gains 1. So the valence of E 2, the valence of chlorine 1. So the interchange, E picks the 1, chlorine picks the 2, and this becomes E chloride, and that is the formula. Then after writing the equation, I should ensure it is balanced. E1, E1, Cl2, Cl2, and the equation is balanced. No more balancing, and this gives me 1 mark. Moving to the next question. Question number 6. The setup below was used to prepare nitric 5 acid. Because it is the setup that we use to prepare nitric 5 acid in the laboratory. And we use glass apparatus, and if you can remember, these are glass apparatus, all of them. we use glass apparatus. During preparation, we have a round bottomed flask. We have potassium nitrate and we have source of it. A retort, glass retort. We have glass topper. No plastic in this setup. Then we have substance N. And then we have preparation of nitric 5 acid. And there is tap water here, meaning this acid is first collected in form of a gas, which is later condensed to a liquid. So, looking at the questions, give the name of substance A. Students, nitric 5 acid is prepared in the laboratory by reacting sulfuric 6 acid with sodium nitrate or potassium nitrate. In our case, we are given potassium nitrate, so we are going to use potassium nitrate. So, substance N, which is in liquid form, is sulfuric 6 acid. Sulfuric 6 acid. Write an equation for the reaction which takes place in the retort stand. We have potassium nitrate. Potassium nitrate. In this case, potassium nitrate is a solid. And we react it with sulfuric 6 acid, dilute, aqueous, and we obtain an acidic salt. In this case, we shall obtain potassium hydrogen sulfate. Potassium hydrogen sulfate. And potassium hydrogen sulfate, the valence as a valence 1. So this is again a solid. We collect it in form of a solid because of high temperatures there, and we then obtain nitric 5 acid, which is aqueous. This preparation is based on sulfuric 6 acid being less volatile, and it's able to displace the salt of a more volatile acid. So we have potassium nitrate, which is a sort of nitric 5 acid. So you can see sulfuric 6 acid displacing the salt of nitric to obtain potassium hydrogen sulfate, and then we obtain the acid, which is nitric 5 acid. So the equation is balanced. We have one potassium on the product reactant side, one potassium on the product side, one nitrogen on reactant side, one nitrogen on the product side, 7 oxygens on the reactant side, 7 oxygens on the product side, 2 hydrogens on the reactant side, 2 hydrogens on the product side, and the equation is balanced. Therefore, this gives us 1 mark. Explain the following. Nitric 5 acid is stored in dark bottles. Why do we, after collecting nitric 5 acid, why do we store it in dark bottles? We know nitric 5 acid, it can decompose in presence of sunlight to produce nitrogen 4 oxide gas. So, to avoid its decomposition by sunlight, so we do this to avoid its decomposition by sunlight. That gives 1 mark. Explain again why no gas is evolved when 0.5 molar nitric 5 acid is reacted with copper 2 or copper tannins. Why is it that when I react 0.5 molar nitric with copper, there is no evolution of a gas? You need to understand that this is a very less reactive, it's a very dilute solution. It's not concentrated, it's very dilute. It's a very dilute acid. And we know copper being less or being very unreactive. It is even below hydrogen in the reactivity series. There's no way copper can displace hydrogen in a very dilute acid. Remember, for copper to react with any acid, it is copper displacing hydrogen from the salt so that the copper picks the hydrogen. The copper picks the sulfate, the nitrate, and then the hydrogen is evolved as a gas. So in this case, we say copper is below hydrogen in the reactivity series, and thus it cannot react with dilute nitric 5 acid. So we say copper is below hydrogen in the reactivity series. Thus it cannot react with dilute nitric 5 acid. Thus it cannot react with dilute nitric 5 acid. And not only nitric 5 acid, but with any other dilute acid. Copper is below hydrogen in the reactivity series. So if I was to react copper with any acid which is dilute, there is no way copper can displace this hydrogen from this acid, so that it picks and forms copper 2 nitrate. So because hydrogen is more reactive, in other words, it cannot be displaced from that acid by copper because copper is below hydrogen in the reactivity series. And that's the reason that reaction cannot proceed, because this particular solution is a very dilute solution of nitric 5 acid. This statement gives you 2 marks. Moving to the next question. A factory uses nitric 5 acid and ammonia gas as the only reagents or reactants for the preparation of fertilizer. If the daily production of the fertilizer is 4,800 kilograms, determine the volume of ammonia used daily, given that the relative atomic masses of nitrogen is 14, the relative atomic mass of oxygen is 16, hydrogen 1, and the molar gas volume is 24,000 cubic centimeters. It is what we say 24.0 liters. So we are supposed to determine the volume of ammonia gas used, and remember, we are just given the production or the fertilizer that was produced 4,800 kilograms. So here we have to start by writing the equation that led to the production of the fertilizer, and in this case we reacted ammonia gas reacted with nitric 5 acid, which is aqueous, and this gave us ammonium nitrate. Ammonium nitrate in our case, let's make it a solid because we are looking at the mass of the acid. In this case, of the fertilizer, the equation is balanced. We can see nitrogen R2, hydrogen 3, 4, hydrogen 4, oxygen 3, oxygen 3. So the mole ratio is 1 is to 1 is to 1. Let's agree on that. The mole ratio is 1 is to 1 is to 1 because later we shall be determining the volume of ammonia gas. And remember, we are only given the amount of this fertilizer that was produced. So we'll first determine the moles of this fertilizer. The moles that were in 4,800 kilograms of this fertilizer. So I'll start by working out the moles of ammonium nitrate produced. So moles of ammonium nitrate produced. So these moles, I start by working out the RFM of ammonium nitrate. The RFM of ammonium nitrate, which is given by 14 times 2, 14 times 2, because nitrogens were 2, 1 times 4, plus 1 times 4, plus 16 times 3. 16 times 3. And this gives me 80. Remember, relative mass has no units, but there's a point I'll use the units. So, after knowing the RFM or relative formula mass, which is always equal to 1 mole, relative mass is always equal to 1 mole, I will ask myself, I use the first principle approach and try to work out this question without using any formula. First principle approach in moles does not require use of formulas. So if I know the RFM is equivalent to 1 mole, then I'll ask myself, if 1 mole of ammonium nitrate is equivalent to 80 grams. Allow me now to use grams because I'm now working out the mass or the moles in these masses. I'll ask myself, what about 4,800 kilograms? But I'm using grams, so I multiply by 1,000. So I'll ask myself, what about 4,800 times 1,000 grams is equivalent to what? Now, after obtaining that, it will be 1 mole multiplied by, it is 4,800,000 divided by 80. When I work it out, I obtain 60,000 moles. Don't be worried. 60,000 moles. Yes, it is correct because 1 mole is equivalent to 80 grams. So what about 4,800,000 grams? So because my aim is to determine the volume of ammonia gas, I'm not interested now with the ammonium nitrate fertilizer that was produced. I'm focusing on the ammonia. Now I come back to the formula. Ammonia plus nitric 5 acid, I obtain ammonium nitrate. The mole ratio is 1 is to 1 is to 1. And this means that if I produce 60,000 moles of ammonium nitrate, then for ammonia, it will still be the same number of moles, 60,000 moles. So if that is the case, I'll just use again the first principle approach and say, if 1 mole of ammonia, if 1 mole of ammonia is equivalent to, remember I'm now using the molar gas volume, which is again, molar gas volume is always equivalent to 1 mole, is equivalent to 24,000 cubic centimeters. So I want to determine the volume in 60 moles of ammonia. 60 moles of ammonia. So when I work it out, I shall have 60,000 multiplied by 24,000 cubic centimeters, and I divide by 1. When I work it out, I obtain 1,440,000,000. I'll obtain 1,440,000,000. 440,000,000 cubic centimeters. So this answer would be correct because they were not specific, the units that we are supposed to use, and because we are given cubic centimeters, we can leave this answer at point. But we can simplify and give it in liters. So we know 1,000 cubic centimeters are equivalent to 1 liter. So I can divide by 1,000 and I obtain it in form of a liter. So this becomes 1,440,000 liters. Liters, we can still use cubic decimeter to represent liters. Learners, this is the correct answer to this particular question. This is the correct answer, and this gives you 3 marks. Moving to the next question, Roman 5. Give 2 uses of nitric 5 acid. Where can we use nitric 5 acid? Nitric 5 acid is used in making nitrogenous fertilizers. Used in manufacture or making nitrogenous fertilizers. Nitric 5 acid can also be used to manufacture of explosives such as trinitrotoluene or TNT, used in manufacture of explosives. We can also talk of manufacture of dyes and drugs, and also in purification of some metals, for instance, silver and gold. So any 2 gives you 2 marks. Moving to the next question. We move to question number 7. In an experiment to study the rate of reaction, excess calcium was reacted with 50 cubic centimeters of 1 molar hydrochloric acid. So calcium reacted with dilute hydrochloric acid. The volume of hydrogen liberated was collected in a syringe and recorded in the table below. Then we have the table. At 0 seconds, the hydrogen gas that was produced was equivalent to 0. At 10 seconds, 60 cubic centimeters of hydrogen gas was produced. At 20 seconds, 90 cubic centimeters of hydrogen gas was produced. At 30 seconds, 105 cubic centimeters of hydrogen gas was produced. At 40 seconds, 112 cubic centimeters was produced. At 50 seconds, 116 cubic centimeters were produced. At 60, 118 cubic centimeters were produced. At 70, 120 cubic centimeters were produced. And at 80, it also remained to be 120 cubic centimeters. So we can try to observe the table, and we notice that there was an increased rate of production of this gas between the 10th second and the 30th or the 40th or 50th second, but there was a gradual decrease in the rate between the 5th and the 60th, and then at 70 it remained 70 to 80, the rate remained at constant, or the amount produced remained at constant. And that means that reagents were fully utilized. And that's the reason the amount of gas production remained at constant level. So from this table, plot a graph of volume of hydrogen gas against time. So without wasting much time, we plot this graph. On my y-axis, I'm going to have the volume. So I'm going to have the volume on my y-axis. Then on my x-axis, I'm going to have the time. So I can now try to plot. So on the x-axis, I have time in seconds, and on my y-axis, I have volume of hydrogen, volume of hydrogen in cubic centimeters. We have 10, 20, 30, 40, 50, 60, 70, and then we have 80. I have started from the margin here, but will allow me to proceed with that scale. Then for the volume, the largest is 120. So if I choose 15, so I have 1, I choose 15, this becomes 15, 30, 40, 45, not 40, 45, 60, 75, 75, 90, then we have 100. 0.05. Then I have 120, 120. I have 120. Then I start plotting 0, 0. So this is 0. So 0, 0 will be at that point. At this point. Then we have 10, 60. 10, 60. 10, 60. 60 is at this point. Then we have 2090, 2090. Then we have 105, 105. Then we have 112, 112. We should know that one small square, if 10 is equal to 15, if 10 are equivalent to 15 cubic centimeters, if 10 small squares is equal to 15 cubic centimeters, then 1 will be 1 times 15 divided by 10, and it will be 1.5 cubic centimeters. So in this case, I need 112, 1.5 times 8. So I'm going to have 8 small squares. 8 small squares from 105. 8 small squares. So we have 108. So I have 8 small squares, but below the 8th one. So we have somewhere here. Then we have 116, 116 somewhere here, and then 60, 118, 118, somewhere there, and then we have 70, 120, 120. So if I was to plot this, I'm going to have, I'm going to minimize. So that I have a smooth curve. So please, learners, take note of my scale. It's not the most appropriate. For your case, make sure you do or you begin your scale from this point. Let your y-axis start from this point so that your scale fits well as you draw this particular graph. Let your scale begin from this point for the y-axis and for the x-axis. For the x-axis, you can do it at this point, or you try at this point. Try to see before you make a decision where you are supposed to begin having your graph. Now, let's dive to the questions. For this question, the axes have a mark each, labeling the axis. The curve, 1 mark, and plotting, 1 mark. So we have plotting, 1 mark, curve, 1 mark, and axis, 1 mark. Total 3 marks. Moving to the questions. From the graph, determine the volume of hydrogen when T was equivalent to 36. So we'll determine when time was 36. So we have 10 representing 10 seconds. So at 36, we determine time at or volume at 36 seconds. So at 36 seconds, let's try to see at 36 seconds we're going to have what? So it will be marked based on your graph. Please take note of that. So if I read my 1 small square representing 0, 1.5, then I have how many small squares? I have 1, 2, 3, 4, 5. So 5 times 1.5, 5 times 1.5, 7.5 plus 105 is equivalent to 110. So that is my answer, 110.5 cubic centimeters. Then the time when the volume is 100 cubic centimeters. The time when the volume is 100 cubic centimeters. So we move to the volume. At 100 cubic centimeters, from 90, we need around 6 small squares. So 6 small squares from 90 shall be at this point from 90. Then we move downwards. Please note that you should be very accurate on our paper. So if I try to check my time at 100, then it becomes 26. It becomes 26 seconds. It becomes 26 seconds. So the answer here becomes 26 seconds. Please take note that you should be you'll be required to show on the graph for you to score this one. If it is not shown, then the assumption is that you copied your answer. So if you use these dotted lines to make sure that the examiner sees where you read that particular value. So that is the correct answer. According to my graph, according to your graph, you might get something different but somehow close to mine, and it will be marked based on the scale that you used. Next question. State two factors affecting rate of a reaction. We have several factors that affect the rate of a reaction. The reaction rates topic, we learned several factors that affect a rate of a reaction. And one of the factors, we have concentration. When concentration is altered, the rate may decrease or increase. We also have temperature. We also have pressure for gaseous or for reaction that involves gases. We also have surface area. We also have catalyst. Catalyst affects rate of a reaction by lowering the activation energy. So any two of these gives you 2 marks. Next question, what is dynamic equilibrium? So we also have dynamic equilibrium under the reversible reactions, especially in gases. And dynamic equilibrium is a state of balance in which the rate of forward reaction is equal to the rate of backward reaction. Is a state of balance in which the rate of forward reaction is equal to the rate of backward reaction. This statement gives you 1 mark. Part 2 of this given question, dinitrogen tetraoxide and nitrogen peroxide exists in dynamic equilibrium as shown below. You can see the dinitrogen tetraoxide here, it is yellow in color, and the nitrogen peroxide is brown in color. We have the reaction being endothermic. Then we are being taught that state and explain the effect of eating the above mixture on the equilibrium. We need to understand that the forward reaction, this side here represents the forward reaction. Forward reaction. So the forward reaction is endothermic. So according to the Lecheterius principle, that when a change in condition is applied to a system at equilibrium, the system moves so as to oppose that change. So forward reaction is endothermic, meaning the temperature of the system are down. Increasing temperature, it will move to the side which leads to decreasing the temperature. Backwards or backward reaction is exothermic, because if forward reaction is endothermic, the opposite is true. The backward reaction will be exothermic. So if I increase temperature, the system will, or the equilibrium will shift to the side where the temperatures are low, because I'm increasing temperature. So increasing temperature will make the equilibrium to shift to right. It is right, and it is left. So with that, if I increase temperature, the equilibrium will shift to the right, not left, because Forward reaction is endothermic. Increasing temperature will favor the forward reaction, and forward reaction is on the right hand side, or is proceeding to the right. So we say the equilibrium will shift to the right. That is, we state that observation. State the observation, state the effect, not an observation. If it was observation, it focus more on the colors, but now state the effect. The equilibrium will shift to the right. The equilibrium will shift to the right. So after saying that the equilibrium will shift to the right, you can now explain why will the equilibrium shift to the right. You can say that forward reaction is endothermic. Forward reaction is endothermic, and hence increasing temperature, and hence increasing temperature favors the endothermic reaction. Favors the endothermic reaction. Favors the endothermic reaction. And of course, the observation that will be made is that the brown color intensifies. The brown color intensifies. So that this information is enough because we are just told to state and explain the effect. So mentioning the colors is not very much necessary, but you can still mention after you have already stated this or given these two statements. So this statement gives you 2 marks. Students, this marks the end of our presentation. If again you found this presentation helpful to you, share this video. Subscribe to this channel if you are new to this channel. Comment your reactions on the comment section. And most importantly, if you have not joined our community, click to our channel and then click the join button for you to get exclusive offers of revision materials, examination papers, and special moments of consultation when need be.